So actually today we are going to start talking about blockchains, right? So earlier in the lectures, we covered Byzantine Broadcast. And Byzantine Broadcast, as we saw, the definition was single shot, meaning you reach consensus once and then you're done, right? And then, I want you to think about a practical system like Bitcoin or Ethereum. So these are like cryptocurrency systems. But by the way, how many of you have heard of Bitcoin? Please raise your hand in the participant tab. Hold on, I think I need to like put the participant tab on my big screen so I can see. Okay, so half of the class raised their hands. Okay, and then how many of you, like if you have owned Bitcoin or any cryptocurrency at any point of time, please keep your hand raised. So only a couple. Okay, so for those of you, it sounds like, maybe not everyone has heard of Bitcoin, but Bitcoin is like a cryptocurrency, right? So essentially it builds a public ledger and the ledger is maintained in a decentralized fashion without having to trust any central party, right? So like maybe a good point of comparison is something like, let's say, Facebook credit, right? So if you use Facebook credit, that's kind of like a digital currency, but it's like controlled by a single entity, in this case Facebook, and then in Bitcoin, the trust is completely decentralized, so you don't have to actually trust any central authority. So like it doesn't matter if the single party becomes corrupt and alters the your account balance on the ledger, right? And so in Bitcoin, the core protocol that the players run is essentially a consensus protocol. Okay, and in Bitcoin, essentially, I mean, it's obvious that you don't reach consensus just once. What you want to do is to reach consensus repeatedly over time. Okay, so that's why we call it a blockchain, right? Blockchain is the modern new name, right? So what is a blockchain? It's a chain of blocks. But classically, this was actually often called state machine replication, right? So it turns out like blockchain is not a new abstraction, like it has been studied for more than 30 years. And the classical name was state machine replication. So we'll just call it blockchain in this course. And then what we are going to do today is we are going to formally define the blockchain abstraction, right? And then we'll try to relate it to what we have already learned, like, what is the relationship between a blockchain and something like Byzantine Broadcast, like which is single shot. And then, after today's lecture, like we'll know formally what a blockchain is. And then, for instance, in the next lecture, we are going to construct a really simple blockchain protocol called Stringlet. Okay, so before I define blockchain, I want to kind of generalize the network model we discussed earlier. So far in our lectures, we have assumed a fully synchronous model. And in a fully synchronous model, if an honest player sends a message, then essentially the honest recipient will receive it at the beginning of the next round. Okay. So yeah, by the way, actually, if you can, please turn on your video and then so I can see you. Okay, so all right. And then more generally, like, you know, essentially if an honest player sends a message, it takes like some number of rounds for the message to be received by the honest recipient. So like in a more generalized synchronous model, right? So we are going to like use a parameter delta, and the delta is often called the maximum network delay. And what this means is that in our network model, right? So the assumption we are going to make is the following. So if an honest player sends a message in round R, then an honest recipient receives the message at the beginning of round R plus delta. So in general, like in the fully synchronous model we have considered so far, essentially delta is equal to 1. But you know, in today's lecture and maybe going forward, oftentimes we are going to assume delta is like, you know, a natural number, but it doesn't have to be 1.
Wait, so just to make sure, it's the honest recipient will receive it at exactly the beginning of round R plus delta, or no later than the beginning of the round R plus delta.
Actually, you're right. So that's a good point. I misspoke, right? So thanks for pointing that out. So actually what I mean is that honest recipient will receive it no later than the beginning of round R plus delta. You know, it's too early in the morning. Okay, so that's very important. No later than. Okay. Okay, so this is the network model we are going to work with, right? So that's kind of simple. It's just a generalization of what we already saw earlier. Okay, so with this, we are going to define what the blockchain protocol is. So blockchain definition. So what is a blockchain, right? Like in Bitcoin and Ethereum, there's a set of players and they're trying to agree on a linearly ordered log of transactions. And this linearly ordered log is often called a blockchain, right? It's a chain of blocks. And a block is like essentially a batching technique, because oftentimes you don't want to confirm one transaction at a time. You want to confirm a batch of transactions together. So you group them into the same block. And over time, you know, you are confirming more and more blocks, and you concatenate all of them together, and this gives you a blockchain. So okay, so in such a protocol, you know, what is the input and output of the players, right? So essentially, a blockchain protocol is actually a long-running protocol, right? And we can imagine that in every round, the players may have input, right? So like in our single shot consensus earlier, at the beginning of the protocol, the designated sender has an input and everyone else doesn't have input. But in the blockchain protocol, we are going to imagine essentially in every round, at the beginning of every round, every player may receive some input. Every player receive some input. And I'm just going to denote the input as TXS, right, which stands for transaction. So imagine the input you receive is a set of transactions that you want to be confirmed. Like, you know, if I want to buy coffee, what I will do is I will submit this transaction to the network, and then the honest players will receive this transaction from the network, and then these will become the input to the blockchain protocol. Okay, and then what about the output? Essentially, the nodes are maintaining a log over time. So we can imagine there's an output in every round of the protocol. So imagine every round, player I's output is, let's say it's denoted log IR, right? And the log is like a, you know, a blockchain, right? And so sometimes this is also called the finalized log. So whatever is output, you can think of it as finalized. So everything in the finalized log, you can treat it as confirmed, right? So if, let's say, I give 50 Bitcoins to Junxi to buy her Ferrari, right? Once that transaction becomes part of the finalized log, it can no longer be undone. So at this moment, it is safe for Junxi to ship me the Ferrari, because the transaction is going to, you know, be there. Like it's not going to be erased later. I won't be able to double spend the coin later, right? Once it's confirmed. Okay. So one thing we are going to assume about the syntax, right? So let's make an assumption about the syntax. Essentially, we are going to assume every honest player's log never shrinks. So the syntax says, like, you know, if you take my log in round R and my log in round R+1, right? The log in round R+1 has to be at least as long as the log in round R. So this is without loss of generality, because if ever I want to output a shorter log, I can always like take the longest I ever wanted to output, right? So essentially, for the same player, we are going to assume log I R prime is at least as long as log IR if, let's say, R prime is greater than or equal to R. So it can never shrink. So that's just like something nice we want from the syntax, because it doesn't make sense for the log to become shorter. Okay, so now this is like the input and output format. And now like we want to define the security properties that we care about. So what are the security properties? There are two important security properties, right? So now let's consider the security definition. So first, obviously, we care about consistency, right? You know, if these multiple players are maintaining this public ledger, it's important that we agree on what the account balances are. Like it cannot be Junxi thinks I have, you know, 10 Bitcoins, but I think I have 1,000. So that's not okay. So how do we define consistency? For any honest player, I and J, right? And for any round numbers T and R, we require that it must be that, so either your log is a prefix of mine or mine a prefix of yours. So let me write it down first and I can explain this notion a little bit more. Or okay, so notice that here, this notation means is either equal to or prefix of, is equal to or a prefix of. Okay, so let's think about what this definition says, right? Because like, you know, the network has some delay, so maybe you have a better network connection than me. And in this case, your log will grow a little faster than mine, and that is perfectly okay. But, you know, at any point of time, it must be that your log is a prefix of mine or mine of yours. So in other words, we agree on the log, right? So when if my network is slower, when my log finally grows, it'll be the same as yours. Okay. So one thing to point out is actually in this definition, I didn't specify whether I and J are the same player or different players. And in fact, we allow both, right? So if I and J are different players, it means like either your log is a prefix of mine at any point of time, or my log at any point of time is a prefix of your log at any point of time. But it can also be the same player, right? If I and J are the same player, it means like, you know, my own log, I have consistency with myself. Like I have to be consistent with myself in the future. Like I cannot like overwrite any part of my own finalized log. But remember also my own log never shrinks, and we require that from the syntax, right? From the syntax, we assume my own log never shrinks. So this consistency requirement, like when I and J are the same player, essentially it requires my log to like be append only. Like I can only append to my own log. I cannot like go back in time and rewrite some of my finalized log. Okay, so the thing to keep in mind, one note is that in the above, I and J can be different players, but they can also be the same player. Can either be different players or the same player. And regardless, this consistency notion should hold. Okay, so that's consistency, like it's a very natural notion. Any questions at this point? Okay, no question.
I had a question.
Yes, go ahead.
I want to know, like, we're assuming that like all messages are reliably delivered within this time, and there are no network partitions, and that all honest nodes are always participating.
So we are actually still working at this point. I haven't defined any other model yet, right? So we are still working with the synchronous model. Okay, like the only thing I did was I generalized the synchronous model to arbitrary choice of delta. But indeed, later in this semester, and actually starting from the next lecture, we are going to talk about a new model where there's no bound. There's no like, you know, a priori bound on the maximum network delay. And even like we want the protocol that guarantees consistency, like even when the network can be badly partitioned, like, you know, even when players sometimes may not be able to talk to each other. Okay. So that's a great question. I think one of my devices is having some technical problems, but I'm still online, right? Like I cannot see you anymore. But let me see if I can fix the problem. Okay, there we go. So let me again put your videos on my big screen so I can see you. Okay, that worked. Okay, so that's consistency. It's a very natural notion, but technically to define it precisely, I mean, still required some thinking. Like there's some subtleties, like you have to be consistent with your future self, and then we dealt with that, essentially by requiring in the syntax. Requiring in the syntax that any player's log should never shrink, and then the consistency definition, right? Like cleverly takes care of like self-consistency by allowing I and J to be like the same player. Okay, so if we only require consistency, then like it wouldn't be too interesting, because I mean there's a trivial protocol that obviously always satisfies consistency, right? And what is the trivial protocol? I mean, of course, we can just have a protocol where no one outputs anything, like our log is always empty, right? From beginning to end, I'm just going to output an empty log, and then obviously everyone will all be consistent. So we don't want the definition to like, include these degenerate protocols. So therefore we need another notion called liveness. So I'm going to define it as tconf liveness, and this tconf is just a parameter, right? So this is like the confirmation time. So let's see what this definition says, right? So, if I buy coffee, I want to make sure my transaction appears in every honest player's log fairly quickly. It's not like I want to wait forever for my coffee, right? So we can formalize this intuition and define it as the following. If an honest player receives some transaction, some TX, as input in some round R, then by the end of round R plus tconf, all honest players finalize logs must include TX. So this transaction will show up in all of the honest players finalized log, in tconf, which is like one confirmation time. And so obviously, tconf doesn't have to be a constant, right? We will allow tconf to be, let's say, a function in, I mean, it can depend on the network delay, obviously, right? What else can this depend on? Like it can depend on, let's say, the number of players. Okay, so if you think about this coffee scenario, if I want to buy coffee, I submit a transaction to the network. The transaction gets propagated to every honest player, and then they will input it into their blockchain protocol, right? So let's say Junxi receives it in round R, and then this means, after T confirmation amount of time, my coffee will get confirmed. Okay, any questions so far? So this is kind of, yeah, go ahead.
It also depends, if it could also depend on the number of players. Like, doesn't that impact the network delay as well?
Yeah, so sometimes delta can also be a function of n. That's also possible. Delta need not be a constant either. Like, and this really depends on how the underlying network works, right? In some cases, the underlying network, like if you have n players, and the n players are distributing messages over a tree, then like for instance, for let's say Junxi to talk to me, we may take log n, something like proportional to log n number of rounds because we are going down the path in the tree. So delta can essentially also be a function of n too. Okay, yeah, thank you so much for that question.
Well, I was actually still a little confused. I'm like, so would you be able to have a tconf that was only dependent on the number of players?
Would you be able to, in general, like if the network delay can be delta number of rounds, like you would need at least delta rounds. Like for instance, let's say Junxi is like the first player who receives this transaction. And even if for other people to see the transaction, it takes another delta number of rounds. I mean, the transaction can contain some, let's say, random string in it. And then, like this random string is unpredictable. Like for other people even to see the random string, it may take delta rounds, right? So in this more general network model, like typically we assume like the adversary is allowed to delay the message, but no more than delta rounds. So like it can choose, between 1 and delta, like, Junxi sends a message to me and the adversary can choose, oh, I receive it in the immediate next round, I receive it in 2 rounds, I receive it in 3 rounds, or I receive it in delta rounds, right? So remember the simulator I asked you to build right there, like the adversary can influence the decision of the network module. So you can think about it that way. So typically it takes, it's like if all the transactions can contain random strings, like, it takes at least delta number of rounds for other people to even know about the string. Like there's no way you can guess the string on your own except with negligible probability, like if the random string is long enough.
Okay, that makes sense.
Okay. So that's a good question. Okay, so that's like the abstraction, right? So we talk about, Bitcoin blockchain consensus. So what do we actually precisely mean? And this is like what we precisely mean. And so for the rest of the lecture, like since we have defined a blockchain, like, the first natural question to ask is how is this related at all to what we have learned so far, which is Byzantine Broadcast, right? Are there any relationships between these two abstractions? And that's what we are going to do for the rest of the lecture. We are going to show that, yes, indeed, I mean, these abstractions are related. And then we are going to ask another question, right? If like these two abstractions are kind of, at least in some models, equivalent from a feasibility perspective, then why do we need 2 abstractions? Why don't we just like study 1 abstraction? And then we're also going to try to answer that question. So, okay. So first, the obvious question is like, we've learned how to construct Byzantine Broadcast. So if we know how to construct Byzantine Broadcast, can we now construct a blockchain protocol, like satisfying the abstraction we have defined? Okay, so we are going to show Byzantine Broadcast implies, let's say, a blockchain protocol. And I want you to take a moment to think about, like, how to get a blockchain protocol. Suppose we know how to construct Byzantine Broadcast. So this is one shot, right? For this, you need to repeatedly reach consensus over time. And what is the most natural idea?
So in each round, you just broadcast your input.
Mm-hmm. Yes, so that's a great idea, right? So like one approach is, let's say in every round, every player invokes a Byzantine broadcast protocol to broadcast their input. And then the output of the blockchain protocol can just be the concatenation of all of these broadcast instances, right? Does everyone see Ke's suggestion, right? Okay. So I'm going to write down a slightly different protocol. I mean, it's essentially the idea that Ke suggested, but I'm going to write down a protocol that is like sequential composition, right? So the one that Ke suggested is parallel composition, right? Because in the same round, you would be spawning n instances of Byzantine broadcast, right? You know, there's one instance where each player is the sender, and then you just concatenate all these instances, the output of all these instances in some canonical order. So that there's no particular reason why I'm choosing to write down the sequential protocol. I just want to like write one that's consistent with the textbook. So we could also just write down Ke's protocol too. Okay, so in the sequentially composed version, okay, so we are going to do this by sequential composition. So the idea is that every time, so every time I observe a transaction, a new transaction, I will like, I want to input it to my own broadcast instance, but I also want to let everyone know that, you know, I've seen this transaction. So first, the first thing I will do is every time I observe a player observes a fresh unseen transaction, and so this transaction can either be received as input or received from the network. Okay, so in this case, I will just like send this transaction to everyone. So like everyone will see it too. And then, okay, so in every round, R, that is a multiple of capital R. Let me define what capital R is. So capital R is the round complexity of BB, right? So let's say this is the round complexity of the Byzantine broadcast. And remember, like for instance, the Dolev-Strong protocol we learned, right? So there, what was the round complexity? It was, you know, f+1 number of rounds, right? So in that case, R is equal to f+1. So I mean, the only reason I'm doing this is because I want to do sequential composition. So I want to like finish the previous instance first before spawning the next instance. So this way, it's a little bit easier for me to keep track of, because like, you know, at any point of time, there's only one instance running. Okay, so every time it's like a multiple of R, I will spawn a new BB instance. Who's designated sender. So we have to specify a designated sender, right, for this BB instance. And I'm just going to do the simplest policy, right? I will let, I will just do round robin, right? In round KR, I will let the leader be, the designated sender be player K, but I have to take mod n because there are only n players. So let's assume the players' ID are from 0 to n-1. Player ID is like 0, 1 to n-1. So when I take mod, it gives me a number from that range. Okay, so this just means we are going to be round. We are going to round robin and take turns being the leader. Okay, so for convenience, I will call the BB instance spawned in round let's say KR, and I will denote this as BBK. This means that it's the kth Byzantine Broadcast instance. Okay, so when I say, okay, this will be the designated sender, right? This player will be the designated sender. I also want to specify what input this player uses during this Byzantine Broadcast instance. So again, it's like the most natural idea. So this player LK essentially collects let's say every transaction it has received, either as input or from the network. So let's, so I want to say, like, what do I want to include here, right, in the message that I broadcast? Like, I want to include everything that hasn't been confirmed so far. So if I have seen the transaction, but it still has not been confirmed, I want to like include that in the message I broadcast. Okay. And so I want to say, but has not been included in its current log, which is, right, what is the current log? The current log is like, I want to make sure the transaction is not in log LK, like during the round KR. So if this has not been confirmed, okay, so let's S denote the set of all such transactions. And now I'm going to input the set S into this broadcast instance. Okay, so finally.
Professor, I think
yes.
Anoop has a couple questions in the chat.
Yes, let me see. So the question is, the BB protocols we studied were defined in the fully synchronous model. Do we need, that's a great question. So, so earlier when we talked about though left strong, right? I mean, obviously it was for delta equal to 1. So how do we take a protocol in the fully synchronous model and get a protocol for more general choice of delta, right? So I'll let you think about it a little more. That's actually something interesting to discuss. So can you take something like though left strong and get a protocol that like works in the more general model where the network delay is at most delta? Any thoughts?
I mean, couldn't you just do the same, but wait for like delta number of rounds before you proceed with the next step of the protocol?
Yes. Was that Lisa?
Yeah.
Okay, thank you, Lisa. Right. So like one trivial approach is I'm going to call every delta rounds a super round, and that super round will be like, one round in the do left strong. So now you may ask a second question, like, then why do we care about this delta model? So in some cases we do care because, like, the protocol doesn't have to do that. Like some protocols, like, you don't always have to like buffer messages for delta rounds and then act, right? Like, sometimes it's better to, I mean, especially in practice, like you don't want to just buffer your messages for delta rounds and only act at multiples of like delta. So it makes sense to consider the more general model nonetheless, because not all protocols have to do that, right? Even though if we can take a fully synchronous protocol and convert it to a protocol that works in this more general model, it doesn't mean that every protocol has to do that. Okay, so that's a great question. And then there's a second question, and then essentially, why can't the adversary send spurious transactions? Indeed, you can. So the syntax of the blockchain protocol doesn't, the application can impose validity requirements on the transactions themselves or how to process the transactions, right? So this is not defined in the abstraction of the blockchain, right? So like by spurious transactions, I mean, maybe there are two different interpretations. Like one is the message doesn't have a valid signature, right? So in that case, like the application can have rules on what kind of messages you can include in the block. And in that case, essentially with the application specific validity rule, this will not be treated as a valid message to include in the block. But there's a second interpretation, like, potentially it's a double spend transaction, because let's say there's some coin, I spend it once by signing some signature, like including the coin ID. And I spend it to buy this Ferrari from Junxi, but now I want to use it again to buy a Lamborghini. So I spend it again with Ke. And so now you'll see in this linearized log, right, there are two spendings of the same coin. And in this case, when the application level processes the log, it'll just discard the second appearance, like, because the second appearance is obviously invalid. So all of this is not included in the abstraction of the blockchain, but it can be taken care of by the application that makes use of the blockchain. I hope that answers your question. So that's actually a very good question. Okay.
Okay, so like if the designated sender in a round like KR is dishonest, they might still propose both those transactions where you're buying a Ferrari and a Lamborghini, but then all the honest nodes will find that these transactions are conflicting and will arbitrarily or they'll arbitrate themselves which transaction to pick.
So yeah, so it depends. So which one is chosen depends on the order in which it appears, right? The only thing we can guarantee here is like that there are two transactions that are trying to spend the same coin, and one of them will take effect, and you cannot really guarantee which one will take effect. It could be actually I submitted this, one of them first, right? Let's say I bought the Ferrari from Junxi first. So like, if you look at wall clock time, I submitted that transaction to the network first, but the network can have delay, right? So then let's say after 1 second, I submitted the second transaction, but it could be like the second transaction got confirmed first. So that's totally possible. And that's why, Junxi should not ship me the Ferrari until she sees it in the finalized log. And the point is, like, once it appears in the finalized log, and she can make sure, there's nothing before it that spends the same coin. If she sees it in the finalized log, and moreover, this is not a double spend transaction, then it is safe for her to ship me the Ferrari. Because at that point, even if the other transaction appears later on, it's just going to be ignored by the application semantics. Does that answer your question now?
Yeah.
Okay. So yeah, thanks for the great question. Okay, so I mean, we are almost
I have a
done.
question. So
Yes,
in
go ahead.
the tconf liveness, we define if an honest player receives some transaction as input in round R. So like, then by the end of round, the honest player will finalize log must include the transaction. So even though the transaction is not from an honest player, they should still see it in the finalized log.
Yeah, so like the system, like right now we are going to assume it's open, right? But the application may have some validity rule on the transaction, like the transaction must have a valid signature, and if you don't see a valid signature, the message is illegally formed, and you can easily filter out all the illegally formed messages. That you can just say, okay, this transaction has to be a string from this space, right? If it's not, like it's not even valid.
Okay.
So but otherwise,
it's not
yeah.
like this level of blockchain deal with. It's the application should deal with the validity of the transaction.
Yeah, so let's assume that, I mean, I guess you can have validity rules that depend on the entire history of the log. You can say, okay, I have a validity rule, and whether this transaction, this Lamborghini transaction is valid depends on whether I've spent the coin before. So that is also okay. But I mean, for now, let's just assume like, the validity rule is defined on the transaction itself. And then when the application processes the log, it can suppress like the duplicates, the double spending of the same coin.
Okay.
I mean, you can do it in other ways too. Okay. Okay, so yeah, thanks for the questions. I think, yeah, this was actually a very important clarification. Okay. So we're almost done with the protocol. I mean, everything is like just the most natural, like we are sequentially composing BB. We are round robin, rotating the leader. And then I just have to define what is the output for every player. So I'm going to say at any time, the output is just concatenating all the outputs of all these BB instances. At any time, suppose BB1, we should probably start from 0. So let's say, K is 0, 1, 2. So I've seen a bunch of instances completed, right? So let's say these are all the instances that have finished. And let's say their outputs are, M1, M2, oh sorry, M0, M1, K prime, respectively. Then the player's output log at this time is defined as the concatenation of all of these outputs. So essentially, at any point of time, every player looks at all the finished instances and concatenates the outputs of all these, finished BB instances, and that is my log. And you can check that the log never shrinks, right? Because, there can only be more and more instances that have finished. Okay, so one thing I want to mention is like, another thing is like earlier when we learned Byzantine Broadcast, we learned it for like a binary value, like people are trying to agree on either, attack or not attack, whether we should have the conference virtually or physically. But here we do actually need a multi-valued Byzantine broadcast, right? So what is a multi-valued Byzantine broadcast? Notice that this designated sender is inputting like some message, which is not a binary value, into the Byzantine broadcast instance. So this is actually a variation of what we have learned. It's called multi-valued Byzantine broadcast. And in fact, in your homework exercise, I asked you to like think about how to construct a multi-valued Byzantine broadcast. So here we are using multi-valued Byzantine broadcast. Okay, so we want to prove that this protocol like indeed respects consistency and liveness, right? So let's say, suppose the BB protocol tolerates F faults, and let's say satisfies consistency and validity as we defined it earlier, right, for Byzantine broadcasts. Then our blockchain protocol, right, satisfies consistency and liveness. Consistency, and I need to specify a parameter for the confirmation time, so I'll write down theta r times n, and we can try to analyze it together. Liveness. So in fact, I think maybe we also need delta, like it needs to be more precisely. Let me write it this way. Also, and it also tolerates F faults. So again, recall that this capital R is the round complexity of the BP protocol. Oh, sorry, consistency. Yeah, consistency and liveness, right? So these are the two properties we want to prove. So the proof is like, in fact, somewhat tedious, but it's kind of good to think through it. And mostly just, you know, we need to get comfortable with these abstractions. So I'll let you think about it like yourself. It should not be like too hard to see the proof.
Oh, will they update their finalize the log in the middle steps? So like we know every R round it's like a Byzantine broadcast round.
Yeah.
Right. So like
So
will they
yeah.
update the finalize the log in something like KR plus, let's say 3? Or
in fact, yeah, that's a good question. I mean, in fact, the way I wrote it, it only updates at multiples of R.
okay.
Like I say, you know, anytime if you see a new instance finish, right, but if you think about it, the new instance will only finish at multiple of R.
Okay.
Okay. So how do we prove? Let's just do them one by one. Like, how do we prove consistency? The consistency should be kind of trivial, right? Like, you know, what are we going to use? I mean, obviously we are going to use the consistency of the underlying Byzantine broadcast protocol, right? So I'm just going to kind of write consistency follows from the consistency of Byzantine broadcast. Because if every Byzantine broadcast instance has consistency, then when we concatenate all the outcomes, we have consistency too. So this is like somewhat uninteresting. Liveness is perhaps a little more interesting to think about, right? I mean, at least there's a parameter involved. So why can we confirm in this amount of time? So what does liveness say? Liveness says if an honest player receives a transaction in some round R, then after T confirmation time, I mean, it should have been confirmed in every honest player's finalized log. So how long does it take to like have this transaction be confirmed? Once like some honest player observes it?
A question, like capital R itself should have a linear factor of delta, right?
Yeah, so I think it's actually, we can omit this delta. This also is correct.
Okay.
Yeah.
Wait, we omit the delta or we make the delta a factor?
Both are correct.
Or-
This is a little tighter. Because like I mean, in some sense, the R should already have the delta in it.
Okay, yeah. So it's like, it might happen that, or the worst case is right after the player K finished his designated round, then he sees this transaction.
Yeah.
So next time he starts, well, after a -1 round.
Yeah,
Or
exactly.
a
So,
-1 times R. And
right.
after he finished his round as a designated sender, it will be Rn. Well, will it be exactly Rn?
So yeah, so let's go over what you said, like more slowly, right? So you said if an honest player, let's call the honest player I, let's say, receive some transaction Tx in round R. Like what is the maximum number of rounds till this player becomes the designated sender again? Like what is the maximum number of like instances for this player to be sender again? So essentially after at most n instances of BB, like I will become the designated sender again. And at this moment, essentially, if this transaction still hasn't appeared in everyone's log, it'll appear after this instance, right? At this moment, if Tx still has not appeared, in, let's say, maybe I should just say everyone's log at the time. Every honest player's log. Then what's going to happen is that I will include Tx in the input to this BB instance, right? And when this instance finishes, this transaction will appear in everyone's log. And when this BB instance finishes, by the validity of BB, right? Recall we have validity, we have to use it somewhere. By validity of BB, Tx will appear in every honest player's log. And then you can calculate, like, how long it takes. And it's not hard to see. It takes at most this many rounds. So in fact, actually, I realized maybe like the first, like for this protocol, specific protocol to work, like this may not be necessary. Like the first action is not necessary. Like even if I don't send it to other folks, I can also just wait patiently till I'm the designated sender, and at that point, it'll be included. So this is an unnecessary optimization if we only need to prove this round complexity. I mean, this is like rather poor. I mean, it's very, very slow. I mean, obviously in practice, this is not the protocol we want to run, right? Because confirmation just takes too long. But right now we are doing this kind of to understand the relationship between these abstractions from a feasibility perspective. Okay, but of course, this is not what you want to do.
What should R be here if we use this?
If you mean capital R, like if we use the left strong, capital R is like F plus 1, right?
F plus 1 times delta?
So, yeah, F plus 1 times delta. Yeah, that's a good point. I always forget the delta. Right? So that can be pretty bad because F can be like, n minus 2, like, it could be 50%. Like if minority are corrupt, it's like 50% times half of n, right? And this is like becomes quadratic. So that's like really, really bad in practice. Okay. So we are going to learn better protocols later on. I mean, this is like not what you want to do in practice. Okay. So that says if you have like a Byzantine broadcast, you can construct a blockchain. And in particular, like notice in this transformation, we don't need any additional assumptions. Like we are going to like, whatever the underlying BB needs, right? If we use the left strong, the underlying BB needs a public key infrastructure. So this blockchain protocol will need exactly the same assumptions. Okay. So in the last 15 minutes or so, we are going to ask, what if you have Byzantine, it's the other way, like which way it is now? If you have blockchain, can you construct Byzantine broadcast? So for simplicity, we can assume like we are working in the PKI model. So we can have like, signatures, everyone's public key is well known, right? So now it seems like this should be the easier direction. Like, we now have repeated consensus and we just want to construct single shot consensus. So how can we make use of the repeated consensus to construct a single shot consensus? So I'll let you figure this out yourself. Like this is very simple protocol. So maybe one of you can tell me how to do this.
I don't think it's that easy because the definition of consistency in blockchain is a little bit different. It says that the log is a prefix of another one, but in BB we actually want them to be the same.
Yeah, that's a good observation.
Wait, but if never mind.
So what's like the most natural idea? So in what we want to construct is like Byzantine broadcast. So there's a designated sender, and this designated sender wants to broadcast a message to everyone, right? And we have a blockchain. So how do we broadcast a message using a blockchain?
Just let the designated sender has some input and let other nodes input be some empty string.
Yeah. So yeah, the sender has some input, and then what does the sender do?
And the sender, and we just run the blockchain protocol, and other nodes has empty input.
Mm-hmm.
So
yeah, so like if the sender, let's say if other people impersonate the sender and try to post message to the blockchain impersonating the sender, like how would you defend against that? That can, like if I impersonate you and I beat you, like, you know, I post my message to the blockchain, so that can potentially violate validity, right? I mean, we want to make sure if the sender is honest, everyone is going to output the sender's message. So how would you defend against something like this?
We have signatures for that.
Yes, that's a great idea. Was that Anoop?
Yeah.
Okay, great, right? So let's combine these ideas, right? And then, you know, the protocol is simple, right? The sender signs its input. Let's call that B, and inputs the signed bit into the blockchain protocol, right? And then what should people output? So if the sender is dishonest, he can, you know, send multiple signed inputs to the blockchain, right? But the blockchain has a consistency property that says, you know, either your log is a prefix of mine or mine of yours. So if I see multiple messages signed by the sender on the blockchain, what do I do? Which one do I pick? Let's say I see two of them. Let's say 0 and 1 are both signed by the sender and they're both in my log. Which one should I pick?
You arbitrarily pick one of them, right? Every honest node picks arbitrarily one when it sees both.
Let's say we should pick the first one, because the honest sender will only send one of them. So you don't want to say, I'll pick the second one, but then then you would require the honest sender to send it twice too, right? Okay, so let's say output the first bit signed by the sender in my finalized log. And everyone does the same. Okay, so that's like a simple protocol. And then the theorem is that, you know, suppose the blockchain protocol satisfies consistency and liveness. Then Byzantine Broadcast should satisfy consistency and validity, right? And it's left as an exercise for you to prove it. And maybe we can do this in the next homework. So that's about as much as I want to say for this lecture. I mean, this lecture is kind of, it's bringing in this new abstraction, right? So once we know what this abstraction is, I mean, later on we can have more interesting protocols. You know, in the next lecture, we'll learn about a really simple blockchain construction called Streamlit. And later in the semester, we'll learn other constructions like Nakamoto's consensus, which is the protocol underlying Bitcoin. And that, is the first permissionless consensus protocol, right? So it uses proof of work. So all of these protocols will prove them to the same abstraction, which is what we define today. And one question that I asked earlier is, we kind of showed that at least in some model, Byzantine Broadcast and blockchain are equivalent from a feasibility perspective. Well, it depends on the model, because I think here we are assuming we're working in PKI. When we go from blockchain to Byzantine Broadcast, we assume the PKI. But at least in some model, they're kind of equivalent. So why do we need this new abstraction? Why not just work with the Byzantine Broadcast abstraction? And I mean, the obvious answer is in practice, we don't want to construct our blockchain protocol by sequentially composing Byzantine Broadcast, because that's going to give us somewhat inefficient protocol, right? Even if you can get it to be more efficient asymptotically, I mean, by no means is this one the tightest. Asymptotically, we can improve the asymptotical efficiency, but nonetheless, if you are sequentially composing multiple instances, it's pretty difficult to perform cross-instance optimizations, right? In practice, when we implement these things, we want to pipeline, do system level pipelining, we want to optimize. And it's better if the blockchain protocol is constructed directly, rather than having to deal with cross-instance optimizations. So that's one big reason why we care about the blockchain abstraction. I mean, there are other reasons, once we have a blockchain, we can define other properties like fairness, game theoretic properties. I mean, these are things that will show up in the latter half of the semester. Okay. Any questions?
Yeah. So I have a question. So
yeah,
I'm a bit confused about the difference between PKI and digital signature. So if everyone know each other's public key, and we have a digital signature, we basically have PKI, right?
So yeah, I guess that's a great question. So PKI is more like a setup assumption, right? It assumes there's a mechanism to distribute people's public key to all the player. Digital signature is more like a cryptographic assumption. We are assuming, in order to get digital signatures, we know that if one-way function exists, we can construct digital signature. So in some sense, we are assuming one-way functions exist. So this is not a crypto class. Maybe that's why I didn't make a clear enough distinction between the two. But when I say PKI, it means it's a setup assumption, that there needs to be a public key distribution mechanism. But with the PKI, you can potentially use other types of crypto. I mean, signature is one way to make use of a PKI. You can, have other primitives that make use of a PKI too, verifiable random functions and others.
Okay.
Mm-hmm. Okay, yeah, thanks.
Thank you.
All right. So I'll see you on Thursday then.
Thank you.